Oh, you can set up, yeah, why don't you start setting up for me? I think I can. No. Hello, everybody. I'm Linda Bushnell. I'm a program officer in the group with Dave and all the other people here for CPS. It's nice to see everyone. I just came in, so hopefully I'll be able to talk to a lot of you later, and also I'm interested to talk to you when I see your posters. So that's great. So I'm here to introduce Jack Stankovic as our first keynote speaker. So Jack's a professor at Computer Science Department, University of Virginia. He's also the director of the Link Lab, and I had the opportunity to go there in April, my first trip for NSF. There's a story behind it with a tornado in Chicago and everything, airport. Anyways, I made it there. It was for the CPS Rising Stars Workshop, which was just fabulous. I don't know if anyone if you know about that, if you can send your students to go there. I hope that was the first one, so hopefully you'll do it again, Jack, because it was really great. It was for postdocs and PhD students looking for how to get involved with the CPS program, and it was really great. And we talked a lot about career stuff and everything like that. Anyway, so Jack is going to give us the first keynote. So he was, he was actually one of the founders of the CPSVO. So I think that we all know Jack. He's been around a long time, contributed to the CPS program. So I think I'll just turn it over to Jack and we can start. All right, thank you.
Thank you. Are you going to show the slides? We did this last night and it worked. No, it's not coming up there. This is connected. It's unless the wrong one. It's not on the screen. I don't have the automatic. Well, while we're waiting, maybe I can, perfect. All right, so it is a pleasure to be here. I'm very happy to give this talk. And, most of the smart health work is focused on things like a particular disease, diabetes or Alzheimer's and so on. Yet, I think that's important work, but I want to take a different kind of overview picture of where we might be in 5, 10, 15 years, where we have kind of ambient intelligence for smart health, and that it's also for well-being, and it has to be general enough that it would handle many different comorbidities that people might have. Linda mentioned this work is done in the Link Lab, where it's a very large CPS lab. We have 40 faculty and over 200 grad students. The faculty are from 5 different departments, and we have put them all together in a co-located space So it's quite a unique experiment that seems to be working well. I do want to make 2 announcements before I get going. So in smart health, a lot of times it's difficult to know where to publish because it's in the middle, right? It's in the middle of a lot of different disciplines. So Insip Lee and I started this journal, an ACM Transactions on Computing for Healthcare, about 4 years ago, and we've been publishing papers for 3 years. And the idea is that we need novelty in the computing, and it's driven by medical issues, but we're not solving medical problems necessarily. And if it's like a pilot study where you're saying, you know, we deployed this and people are getting better, then if there's no computing novelty, then it shouldn't come to this journal. But if there's computing novelty, this is the place to send it. Also, Linda mentioned the Rising Stars. So we did this last year for the first time for CPS students who are graduating or 1 or 2 years from graduating and want to go to academia. So the workshop builds upon ideas about how to go about applying, how to be successful in your search, how to be successful once you get an academic position, trying to also look at underrepresented minorities. And we were kind of surprised because it was the first year ever, but we got over 120 applicants, and we ended up awarding 33, and with 22 different universities. So please keep this in mind when you go back. We should be setting out an announcement roughly in January. The meeting is in May. It was a very, very exciting meeting, and all the new students were really very, very engaged. So we hope to do this again. All right, so if I'm going to talk about ambient intelligence, let me define it. So we think of ambient intelligence as a seamless infrastructure. This is where the CPS part comes in, that integrates in-body, on-body, in-situ sensors, and even actuators for interacting cognitive assistance. This is where the intelligence comes in. So let me give a picture of it. See, here we have, you know, this person here has maybe all sorts of devices on them, sensors, measuring blood pressure, EEGs, and so on. They may also have a smartwatch or a smartphone that is running a cognitive assistant, helping them in their activities. And no matter where they go, whether they're in their smart home or they go to a smart hospital or they go into a smart city over here, then they're interacting with other agents. And these agents are all smart cognitive assistants as well. And so how does one go about building this? I think we're still far away from this happening, but it's, I think a lot of things are in place for it to start happening. To be a little bit more precise with respect to smart health, let me look at an example of the vision that people have for this. So let's say we have this elderly person living alone maybe, and they may have in-body things like pacemakers or maybe take nano pills to do diagnostics once a day, once a week. They might have wearables, smartwatches, pendants, and so on. They could have a smartphone. They're getting so sophisticated and so powerful that they're also could be acting as a cognitive assistant, or the smartwatch might be. There could be sensors and actuators in products that they use. So this walker may detect that the person is starting to fall, tilt to the side, and actuate to push the person back to minimize the probability of a fall. The smart environment you're in may have sensors and associated processing to detect sleep and medication and all sorts of activities of daily living. And you could think of the house as being a smart cognitive assistant, and the person has a cognitive assistant, and those two cognitive assistants are interchanging knowledge and information. If they go out into the real world, again, no matter where they go, they're going to be interacting with other kind of kiosks or robots or other cognitive assistants. Lots and lots of information pushed to the cloud, or even people might be learning information through WebMD and other activities like that, and that information may be downloaded to the person's smart cognitive assistants. The information goes both ways. Some of the information is for the individual, personalized, some's coming from general population. And so we're really trying to see that this is going to include a holistic view of the person's well-being, not just one app to do one thing for one disease, all right? And there are lots of actuations here. It's not the classical feedback loop necessarily, but the activations could represent alarms, messages, interventions, recommendations that closes the loop. All right. And this kind of model is what we're really thinking of as ambient intelligence. And as I said, we're pretty far away, but how are we going to make some progress towards this? So I do have like 5 different parts of the talk, and some people like more high-level ideas, and some like more specific, so I have a little bit of both. And I want to begin with just a couple of slides on some of the key challenges. And, you know, as Dave was just saying, you know, CPS is about the physical world and the cyber world and how these two come together. And in this ambient intelligence, we're going to be in the wild for sure, right? And it's a very non-deterministic, noisy kind of environment. So the sensing has to deal with all different kinds of noise, missing data, multimodal collection of information, sensor fusion, data fusion. We need to understand the physiology of the person, the environmental context of the person, and even the psychology of the person. Like, what are they doing, and why are they doing it, and how do they feel? And this is something missing. That's why I put it in red. Almost all of the machine learning stuff in smart health does not address the psychology aspects of the person in dealing with that particular health problem. We also have to know who the person is, because a lot of the information is personalized. And then we have this expanded notion of what actuation means. And in the cyber world, there's many, many things, and I won't go through the whole list, but just point out the first bullet saying there's realities of the physical world. That's what has to happen. And too much work right now in smart health is done in ideal environments, and they don't really exist out there. And so what we need for this, to move towards this, is we do need a comprehensiveness in the solutions. They have to deal with well-being and disease, but not just one-off solutions. Because after a while, you'll have hundreds of different solutions, and it'll be really a mess to try to figure out when to use which app and everything else. And so the other side is this is safety critical, right? So we need safety. We need guarantees. How are we going to get this from these very non-deterministic environments? And we need continual learning. I think a better term actually is meta-learning. But once the system, if it's running and it's this ambient intelligence is out there, how is it going to continually evolve over time, right? And so you need to continually learn what's going on, both in the environment and for the health issues. So I'm going to briefly say something about 2 different models, 2 challenges, I mean. One is the models, and the other is, I'll call it, interactions between the cognitive assistants. So here's our classical feedback loop, and the target system, you know, usually is modeled, and that model typically comes from electromechanical principles for most of the control theory literature. But what if we need that model to be data-driven? We need more data and not just control laws. And in addition, it has to be robust, right? And so what can we do about that? And we've seen lots of examples where data-driven alone for building models, whether you're using classifiers or machine learning or in control loops, they're very brittle and there's no guarantees, and we can't just live with that. So we think we need to include formal methods and knowledge graphs to incorporate knowledge and properties into the models in a way that you can guarantee that the models will produce something that you want it to produce, and not producing predictions and things that are not realistic. And also, given this environment, we can't have solutions that simply say, you know, it's a cat, right? Here's a picture, it's a cat, right? We need to have some form of uncertainty measures like confidence intervals and things like that. So these last 2 here, I will come back to towards the end of the talk. But I want to mention, if we look at a control loop and we see that model that has to be of the target system and we want to combine machine learning and control, can we do that? And this is work by Maher Bell that was done a while ago, where he combined basically the ability to use a lot of data to build random forests using machine learning techniques, but when you go down the tree, like say this is a particular random forest and you have different context, and you're learning this context through the machine learning, and you get to the leaf, and in the leaf, you actually use system identification from control theory to build models. But the model at that point is very constricted into the part of the system that already has all this context. And this is one way of integrating both, machine learning and control modeling into a new model, and they can fit in those control loops that I showed. Now, what happens if you want to use a CNN or an LSTM instead? So I think there's a lot of room for interesting work in trying to build models this way. Also, interacting agents is going to be the crux of the system. It's the physical side of the system. Agents have to understand the context. Like this person here, again, we have to understand their personal context, their history, their medical conditions, and so on. We have to know where they are and what they're doing and what the environment looks like. We also need to know what their objectives are. If they're going to a doctor's office, it's different if they're going to, out to dinner, right? So they have different objectives of where they're going, what they're doing, and the cognitive assistants should produce decision-making for them and help them. And there may be lots of control loops both here in this robot and in this individual as well. But what I'm arguing is that this interaction needs to take a step up from where we see things today. And I'll call it, we should be exchanging intelligence between the entities, not data, right? So let me give an example. So if you pass raw data, for example, I have physiological parameters on my body, and I'm passing the blood pressure, and I'm passing even my mood and things like that to this agent that I'm interacting with. And that's not really passing intelligence, right? It's just passing data. Then the recipient has to figure out what all this means. Rather than what if I am passing assessments about what's going on. So it's saying like John experiences some medical problem right now, and he needs medication, and he needs stress-reducing actions, and something like that. So it's a level up, and this part, I think, we haven't done very much with this. I'm just kind of identifying this as a really important problem, and so I'm not going to address this in the remainder of the talk, but I think it's a definite challenge, CPS challenge, because you have to collect data from all sorts of sensors and actuators and smart objects in the environment, and use it in a way to build some kind of knowledge about what's going on. All right. So let me move to the second topic, which is related, of course, but the idea is ambient intelligence really hype, or is it going to cause a revolution? And I think it's just starting, to be honest. And we do have smart watches that are becoming very, very prevalent and having more and more capabilities. So we have smart skin, smart textiles, and so on. We have in situ devices and how all these fit together. And the question is, one question is, can we build cognitive assistance on smart watches, for example? So the theme here for the next two kind of parts of the talk is that I want to explain what we're doing with wearables and how this can build cognitive assistance using machine learning and NLP, and then underlying it as a technology requirement is acoustics, because we want people to just operate it normally in the environment, and they're going to be talking a lot and using that as a main modality for intelligence. So I'll talk a little bit about solutions in these two areas. So we built a system. Actually, we have 3 levels of this. It's called iAdhere. It's a verbal medication and an exercise reminder system. And we applied this in a telemedicine setting. It was on an Apple Watch. Stroke patients who went home typically get a list of medications to take and when they should take them, and a list of exercises to do. All right? So if we just do something simple like, okay, we buzz the watch at 9 a.m. and we say, time to take your pill, right? So that's not smart. That's not very interesting. But what if, when we do that, the person can interchange with the watch, could say, which pill is this again? Why am I taking it? Do I take it with water? Do I take it with food? how often do I take it? What might happen if I don't take it? So there's lots of more dialogue about that particular problem. And that's, I think, moving it more towards what we really want the system to be, and not just a simple reminder. The second frame here is about exercise, and there too, if we just said something like, it's time to do your exercises, and they say, okay, I'll do them, that's not very, very useful in terms of a cognitive assistant. But if they can ask questions about the exercise, how many steps, why am I doing this, and provide quality on the exercise. When you do the exercise, just don't say you did it or didn't do it, but look at the quality of the exercise and reply to them about how well they're doing the exercise. We can also integrate, this is an EKG on this frame, so the Apple Watch already has an EKG, so we can just integrate that in. And you're getting some sense that, well, we do medicine, medical information, we do with drugs, and we do exercise, and we do EKGs, and so we're starting to make the platform more and more comprehensive. This last one is if the person, for privacy, doesn't want to deal with it verbally with their smartwatch, they can do it textually by just turning off the voice. This demo, I'm going to cut it off, just the very earliest version, but it gives you a little bit of idea of the exchange that might go on. And but it is 2 versions. I should really update it, but and then the second half talks about the cloud, and we move everything to the cloud. But I'm going to skip that part.
Welcome to the demo of Ambient. So this is a reminder. It's for checking ECG. So I tap on the reminder.
It's the time to do an ECG. Do you want to try it now?
Yeah, sure. Please tell me details.
Okay, press the crown to go to apps. Tap on the ECG app and follow the instructions.
So now I follow the instructions. I go to the ECG apps, and now I can do the ECG. This is the reminder for the.
It's time to take your nightly medications. Take all medications as directed by your physician.
Please tell me details.
Metformin and carvedilol.
Okay, thank you. Can you remind me after 1 minute?
Okay, remind you after 1 minute.
Okay, thank you.
All right, so it's still pretty primitive, but its new versions are much more advanced. But to get the sense of needing to have this different way of dealing with individuals and providing a dialogue system that starts to look like it's intelligent, all right? But including if now we're going to even go further with other services that we need. And when the pandemic hit, there's what other services might we want? So hand washing is important because people were told to hand wash a lot to avoid COVID spread. And we want to detect that, but also the quality of the hand washing, what they're doing. And World Health Organization, specifies a certain pattern of washing hands like this in this way and so on. And so we can build a classifier to detect that. We can detect the mood, people in COVID, isolated, different mood or anxious and so on. We have, again, this voice-based conversation with them where they can ask about where can I get my shot, how many people died today in Virginia, how many died in the United States, how many new cases, so they can, and we go to the web and find this information dynamically and let them interact with the system that way. You can also start detecting coughing and fever and so on and bring that into, a well-being issue where the person is getting sick or not. And the combination of all this in the latest one is called Voice Care. It was published if people are interested. And so this is just a screenshot of the hand washing support, and there's over here, this is a sensor that detects when you come in. So when you come into the house, you would be reminded to do hand washing. And it also has this dialogue system, time to wash, okay. You could say, remind me again later. You did a good job, you did all the steps, including the 20-second total time, or you missed step 3, which is this, you can then show a picture of which step you missed, and that kind of thing. And to solve this problem, though, is not easy. It's really a difficult problem. And our solution has a combination of, here is this lower level is a 3-level CNN, and it has various kinds of attention mechanisms. And this CNN really is good at detecting the spatial relationships between the hands in the different steps. And then this LSTM is the temporal relationships between the different steps and within the step. And so both of those are combined, and then there's even a feedback loop here to use the previous prediction included in the new prediction. And so implementing this, we were able to do some evaluation. We created our own data set. We had 14 participants. They took the system home, the watch with us on at home. We had a video there for ground truth. They were taught how to do the World Health Organization hand washing. And then over about a 3-week period, we wanted them to do 19 hand washing sessions each. And our results, I won't spend a lot of time on this, but our results were called iWash, which is this one here. And you can see it's for different steps in the process. We get about a 10% improvement, at least 10% over the state of the art with these other 3 systems that were available. Okay. The next topic is, okay, so since speech is so important in here, how do we develop ideas about being able to understand what they're saying and also detect emotion, which is a really strong part of health, especially mental health. And so we developed a solution for distance emotion recognition, and we have other solutions for anxiety and depression and so on, but we're not going to present that here. So this gets to the issue of reality in the real world. So if there are people talking in a microphone like I am now, and you want to detect my emotion, we can have algorithms that work very well, right? Or if we're at a table fixed distance from the microphone, we can also do a good job. But that's not a realistic situation, especially not for ambient intelligence. So like if I'm in a home and there's a microphone here on this table, right here, and I might be several meters away, and I may be even further away. There may be 2 people here, there may be 4 people here, all at different distances, and obviously the acoustic signal is affected by reverberation, ambient noise, de-amplification of the speech depending on your distance, and people may be talking at the same time, overlapping speech. Those are all realities from the physical world that have to be handled in your acoustic processing if you're going to have ambient intelligence, all right? So very, very briefly, our solution has 3 parts. We first want to find features that are distance agnostic, and then we're going to encode that into what's called code words, which I'll explain, and then we come up with a different feature modeling technique called Emo2Vec that represents that set of features, and then we just put that into a standard classifier, right? And all of this is done with respect to needing reverberation, de-amplification, and so on. And so the first step was we basically looked at the literature, and the literature used roughly 231 low-level descriptors that I have in this table that represent what seems to work really well when you're near the microphone, right? And these features are 77, but also their delta and their delta-delta come out to 231. And then by various studies we did at different distance from the microphone and so on, we ended up showing that 48 features were less dependent on the distance. So we only use these 48 features. Right? And in using them, we developed, we put them in the form of what called code words. So in this signal here, let's say we have this audio signal, and we look at this first part represented by this little parentheses, and we want to compute the features in this part of the signal, right? That's standard. And I'm going to assume there's only 2 features, X and Y, so I can plot it, all right? But we really have 48 features here. Then we sliding window, we have 48 features here, 48, 48. So we process the signal through with these features. But if we look at this and we compute the features X, Y, and say it plots to this point here. So since it's plotting to that point, that's a representation of this part of the signal, and we do this over and over again, and we end up with groups of points, and taking the centroid of those becomes an audio word. So you have to define how many clusters you want, like when K clustering, K means, and then the centroid becomes the audio word. And then so here we say have word 1, 2, 3, and so on, and if you have C of these clusters, then you have C words in your vocabulary. While you're testing, you might get a signal that has an XY features that put the point here, so we map it to the closest audio word. Right? So it's simplifying the infinite variety of, kind of signals that you can get. Right? And if a second word comes in, then we map to, maybe it maps to the same audio word. So those 2 signals, parts of signals are different, but they're close enough that we end up mapping it to an audio word. And we've tested different code book sizes from 500 to 2,500, and it seemed like we needed different code book sizes for different emotions. So for sad, happy, angry, and so on, it works better for different code book sizes. The other thing is, I don't know if people are familiar with something like word2vec, which is a very standard thing to use in natural language processing. And the idea is you have a word in text, and you want to understand how it fits with other words. And so you would assign it a vector, and the vector represents its relationship with the other surrounding words. And so we have a variation of that called emo2vec, where let's say this is our code word. Here I'm using code words ABC instead of 1, 2, 3. So let's say this is a corpus of happy. So all these represent happy samples. And I have this code word A, and these are the other code words that surround it. And I have another code word B, and these also have almost the same words surrounding it. So then A and B, since they're both happy, their vector representation should be similar. And then on the other hand, we have this other code word C, which also has a very similar context surrounding it. However, C is not happy. So its vector representation should be far away from A and B. Right? So this is how we encode the context of the code words representing the different emotions. And then we just plug that in. So here's my acoustic signal, and here's the first time slice, and we compute these 48 features, and then we get their code words and build this emo2vec feature representation of that, and then put it into an LSTM. And then the next slice goes in, and so on. And then we predict the emotion that way. We did this with data sets from the literature, but also created our own data sets where, using psychologists, they brought people into a lab and they had spontaneous discussions and tried to get them to be happy or sad or angry and so on. And then we also had different baselines from the literature, and we feel like we showed like this solution was about 16% better than the best baseline. Notice that in the past, happy and angry tended to be difficult to separate. And when you do distance agnostic, though, then it kind of removes the volume aspects of the assessments. And so angry and happy are also often very high volume, and getting rid of that energy-based features enables us to be a much better job at dealing with the difference. Also, laughter is something that helps discriminate the two as well. We did ablation studies and so forth. I'll just mention that, like for example, here we have angry and we have, say, the accuracy, and this bar here represents if we use all 231 features, and if we get rid of most of the features and only use 48, we do about 9 or 10% better. So the extra features are hurting you instead of helping you. And overall, the effective distance is important, and as you move away from the microphone, accuracy does drop. And in our case, it was dropping about 5% compared to the state-of-the-art was about 12%. Now, I'm saying acoustics is really important, but I think there's still many open questions. So once we deploy the system in the real world and it's out there, where's ground truth? If our algorithm says the person's sad, is that true? So where's the ground truth at that point? It's a tricky problem, and we have actually some ways of dealing with that, but I think it's still open. Even though we've been working a lot with having solutions that work with noise, reverberation, and distance, a lot more can be done there. Distance can be increased, different reverberation kinds of scenarios, and so on. So I think could be more. We also found in the project we're doing with Alzheimer's patients and caregivers that there's a lot of times that the caregiver is either the son or daughter, and if it's an elderly woman who's got Alzheimer's and the daughter is taking care of them, their voices sound very similar. So father, son, daughter, mother kinds of relationships have not really been addressed in the literature very well anyway, and there's a lot of overlap speech. You train on people, and then people have a cold, or they're really tired, or they're drinking, or they, kind of taking medication. Changes the voice. Where's that? That's real. That's something if you have ambient intelligence, you're going to have to solve those problems. Also, most of the time, the systems on emotion detection for mental health looking for a single emotion. But people have many emotions. There's, in a chart of emotions, there's something like over 60, depending on the paper you read, there's over 60 emotions. And so what if we need to understand the difference between anger and frustration? So under typical features that have been developed in the literature, they're hard to distinguish, and they're lumped together. However, treatments are very different. So we need to figure out how to discriminate between very similar emotions, because the treatments are going to be very different. All right. So now I'd like to circle back to the notion of models and what's important about them. And models basically are going to be central to ambient intelligence, and the models have to be robust because of the safety critical aspects. We want to make some guarantees on the outputs of the models. We want to develop the models so that outcomes that are being predicted give you confidence intervals, not just it's a cat, right? Go back to that. And then the models have to dynamically learn with meta-learning and knowledge graphs, incorporating knowledge and keep updating that over time. So I'm not going to talk about this last one here, the dynamic learning, but I'll try to talk a little bit about what we've done in the other areas. So when I say we want to integrate properties into the models, what does that really mean? Well, physics has actually been doing this for a long time. They have a 10, 12-year history of using data to build models that reflect equations, essentially. Okay, but that's somewhat limited when it comes to the kinds of things we're talking about in ambient intelligence. And so I believe that you can represent knowledge, what's called world knowledge, in knowledge graphs. And many of those are not equations, or they don't fit neatly into even necessarily some formal methods. And for example, if you're doing smart cities CPS work and you want to understand traffic and pollution and how the system responds to emergencies and so on, maybe you need to know that the city has 5 major hospitals and where they are. Okay? And the models may be ignoring that information totally. Or in the health area, you want to predict something about the patient's blood pressure or something like that. And maybe you need to know that parents had dementia. So where is all this information? And so incorporating properties, it really includes all of this. And one way that we're starting to work with this, and actually I think some of the other keynotes might address this later, is that incorporating formal methods with machine learning models. So this is a kind of a busy slide, but let me just kind of walk you through a little bit of it. So here is, just consider the top network. This is a RNN, and it's called a student network. And here are the inputs that are being monitored, and they come into your network, and you make some prediction, and you pass it to the next stage, and you get some new inputs, and so on. And let's imagine you're right here, and you had this past history, and you're getting new inputs about a smart city or about a patient, and you want to predict what's going to happen in, say, 3 time steps in the future. So if it's a smart city, you might be predicting pollution and traffic volume and so on for the next hour. So this might be 20 minutes time steps. And so when I'm here and I'm predicting the future, what kinds of predictions am I making? And are they reasonable? Do they have properties? And so what we do is we have a teacher network that models this, except we add in, using formal methods, a set of properties we want the resultant model to follow. All right? So, for example, the property might be that don't predict that there's more than 50 cars on this street, because physically you can't fit more than 50 cars on that street. And if you don't put that constraint in, then this model, based on data alone up here, would possibly produce some weird results like that. And so what happens is, as you're training, and the student network is producing various outputs and predictions, every time we get one of those sets of predictions even, we compare it to all the models, properties that we're trying to enforce, and then when you violate one of those properties, we adjust the weights so that we end up by iterating to push the weights to a certain way that we do not have predictions that violate these properties specified with formal methods. All right. The notion of uncertainty also is really important, and here's an example in a smart city where, say you're trying to predict traffic volume, and let's imagine that each hour you take all sorts of information, and this is the state of the city at time 1, at time 2, and at time 3, and you're at time 3 here, and you know this past, and now what could possibly happen in the future? I need to predict the future. If I predict one path in the future, and I get just one of these lines, if I look at the real data set for the real city, with this prefix and this current state, any one of these other paths were possible. They happened. So if I don't look far enough back, I get a really large, unpredictable future, right? If I look further back, I get a bit narrower future. If I use more information, I get even narrower. Right? But there's always going to be some uncertainty into the future. And so we want to categorize that uncertainty with confidence intervals. And here again, we can bring in some notions of formal methods to help define what you want and then detect whether or not that prediction is going to satisfy your requirements. So, for example, here at time t, if we have this requirement that says, you know, for all time between 0 and time a, which is here, we want the variable we're testing to be less than lambda. So let's say this is AQI, air quality index. So we want the air quality index to be less than lambda. So here's lambda, and we want the air quality index in the city to always be less. And so at time t, we have trained this model, and it predicts that up to time t, this is the path, where the gray is the confidence interval. So we can see that with that confidence, the pollution is going to be fine all the way up to here as far as we can predict. Right? Now, if we want to know all the way out to time, say, T1, then we can see that as we get further out, the confidence intervals grow, and we can see that from this point to this point, no matter which path we think that might happen, they all violate the pollution requirement. And then here, if we go out even further, we're seeing that sometimes we're violating and sometimes we're not. And so we're not sure, and we have certain confidence level, right? All right. So I think, you know, these are two papers we produced, and I think it shows some feasibility of integrating formal methods and Bayesian deep learning towards accurate estimation of uncertainty. We're trying to incorporate real-world requirements to guide this learning process, and with the ultimate goal of having some resulting system that you have certain properties and guarantees. All right, so the last part I would like to talk about is that if we're doing ambient intelligence with such dynamic, complicated environments, we need to be doing real-world experiments. And Dave mentioned in his introductory remarks, you know, CPS is about doing deployments and doing real-world experiments. And we've done a lot of these, including we had a system we built to monitor family eating dynamics of obese families, and we did this with USC, and we did 23 families over 2 or 3 years in Los Angeles. We had another project with Alzheimer's patients where they had incontinence, and we were measuring that incontinence and when it happens and how it affects their sleep. And then we have currently ongoing Alzheimer patient caregiver interaction, and we're focused on the caregiver, trying to improve the caregiver's stress. We finished 6 4-month deployments, and we have 5 more deployments kind of being prepared. Two are actually started already, and the other 3 are going out. We also did smart hand washing in a pediatrics intensive care unit and also in different homes. And so with this, you know, what are we learning about real deployments? To give this a little context, let me just say, like, here's a diagram of our system for this patient-caregiver relationship. So here we have the patient and a caregiver living at home. Real world, well, sometimes there are 2 caregivers. Sometimes there's a caregiver that comes in once a week. Sometimes, you know, that the caregiver gets sick and so on. So there's lots of realities that have to happen here. We have a kind of extensive acoustic system to detect anger, to detect conflict in the caregiver, and so then we can act on it. And so this acoustic system has kind of all the standard pipeline things in acoustics, like detecting human speech, getting rid of silence, and so on, doing speaker identification to make sure it's the right person, and then detecting the emotions. And then we go to a recommendation system, which is kind of in this part of the chart, where we're using reinforcement learning. We would give recommendations to the caregiver. and it's categorized in 4 different types of recommendation, and each one of those has subcategories, and the people up front tell us what they like the best, and so personalized things are embedded. And then, we go out to interact with a caregiver through a smartphone, through EMA, and so that's the main core of the system. But we do save everything on the cloud, and then we can, analyze all the data there. And we also have our monitoring system that we have to watch the system and make sure it's still working and act on it when things go down. And the system even automatically restarts things if we detect a particular process is down or something like that. So with the system in place and running for, kind of 4 months, which is pretty long in a research system, we found lots of lessons. This is not new. When people often say, expect the unexpected when you go out in the real world. We had one patient who all of a sudden decided to pull all the wires out of the system, and it'd be nice if you had ways of detecting that. The internet, as good as it is often down, especially in rural areas, and so you don't want to lose data, so you have to have ways of making sure that even when the internet's down, you are going to save all the data and then upload it once the internet comes back. You deploy the system with certain assumptions. Those assumptions are going to change. So to be robust, you got to worry about that. People move the system from their kitchen to the den or something without telling us. So it would be good to be able to detect that and determine that that's really happened. So we just assume they would never do that, and that's not the right thing to assume. Over 4 months, the person, they went on vacation. All of a sudden, we're getting nothing. We thought they were dead, like kind of thing, right? So they weren't, and thank God. And they got COVID. Then their voice sounded different, and our classifiers weren't working so well. We couldn't recognize them because their voice was so different. And humans are very complex, so even under exactly the same conditions, they make different choices, right, all the time. And so you need to understand that uncertainty curve and understand that this is going to happen. We also saw that because in our case, many times elderly who have Alzheimer's, it's their children taking care of them, and so their voices are similar. Some people leave the TV on all day, so you have all this TV sounds coming in. If you build classifiers that ignore that problem, you're going to have trouble. There was construction. We tested to build a classifier. We tried to be as rigorous as we could, but we didn't test for construction noise, right? So that affects some of the accuracy. We also found in anecdotal things like, oh yeah, I was in the kitchen and the Alzheimer patient was in the TV room, and I yelled over like, "Do you want lunch?" And that person yelled back, "Yeah, make me a grilled cheese or something," right? And that comes out like they're yelling and screaming at each other, so that is like anger. It's not, right? So that's another thing. I actually incorporated sounds we found from all of our deployments, and I broke them into physiological objects and ambient. And the idea is here is, I'm not going to read through all these, but there's lots and lots of sounds that it's almost impossible to test and build, say, a data set that has all the sounds in it, right? So we need a better way of building the acoustic processing that can ignore all unwanted sounds, right? As opposed to needing to deal with each one separately, which isn't really going to work. And kind of the final thing that I want to mention is that I do feel like we do need a better methodology for researchers like ourselves doing smart health who want to build new technology and then deploy it and see it working. So what do we normally do? This is fairly standard on the left side of the slide. We typically develop new solutions. Many of them often are made machine learning with data sets. We may try to make the data sets as good as possible, incorporating background sounds and reverberation and so on. And then we also maybe then test it in a lab, and when we go to test it in a lab, we find new problems, and we end up having to change what we thought was going to work. Then we maybe even test in trial homes, like the grad students' houses or my house or something, And we end up with new problems that we didn't see before, and we have to fix again. And then we go to the real deployment, and we end up with new problems again, and it's not working, and we have to fix it again. That's not good science, right? So how do we get something where, what can we do at development time, way back here, so that when we deploy, it's going to work? Obviously, other engineering disciplines do this, right? You're not going to build a bridge the way I just described on the left, right? So how are we going to do this? And who's working on that? We've started thinking about this and figuring out, we kind of just wrote a paper on some ideas about how to make what you do at development time really likely to work and minimize the problems you do at, kind of when you actually do the deployment. All right, so let me finish up by just saying that I do think that if you look far enough out, that there will be an ambient intelligence for healthcare. I think it is a long way off. I think it'll work before ambient intelligence in general. Because ambient intelligence in general is so broad that it's like general AI, or say general machine learning. And so that's really hard. But maybe when we focus it on one area, it's more doable. And to do this, we need the intelligence side. So that's why we need the AI and machine learning, and we need the platforms and interactions and support and sensing and control. So that's the CPS side. And these two have to come together. I do think key modality is acoustics, and we do have to worry about privacy for sure. I think a really open problem is, how do we make these systems robust and with properties, and how do they dynamically learn over time? The machine learning community has been working on this for a while. I think CPS people need to get involved and help where we can apply CPS principles to the dynamic learning problems. And so I would like to thank students. There's a list of 5 students. 3 of them are now faculty at other universities, and they did all the work that I described. And I'd like to end with this one, which I like this Spectrum cover sheet where the smartphone is going to see you now. I always wait in the doctor's office, and they always, finally, after like hours, they say, the doctor's ready to see you now, right? But we won't have to wait. We'll have a smartphone tell us that. Okay, so thank you. That's what I have. I'm happy to take questions if there's time.
So we have microphones out there. If people want to ask questions, just step up to the microphone. There's also some Slido. There's a Slido app. I don't know if you guys have to figure out how to get to it from the CPSVO questions. But okay, so we have a question over here in the. Oh wait. Oh, sorry. You can do it.
I think he was first. Go ahead.
Thank you, very interesting discussion. One of the things that seems to be a large problem in the medical field is the impact of new technology on providers, not just patients. I didn't hear much about that, but there has been a lot of complaints by medical providers on just basic medical record systems that have actually been worse than paper files from the provider perspective in time. So I wonder if you and Mark has looked at whether medical providers actually appreciate these contributions, or whether it just adds to their workload and makes their life worse as opposed to better.
Yeah, so that's a very, very good question if you're wanting to, push things out into the real world in a large way at this moment. And so, we haven't really done that. We are looking at things we see that very far out, but I agree that that's a big issue, although if it's a win-win, I think it will go away. So somehow you have to make it a win-win, where it eases their job, not makes it harder. I think it's somewhat related to when 10 or 15 years ago, I went to an assisted living facility and I tried to convince people there to let us put sensors in their apartments. And no one wanted it. they didn't understand it, and they didn't want it. And then I asked, how many would do it if we could keep you out of a nursing home? And they all raised their hand. And then another example is like about 7 or 8 years ago, we went to the UVA hospital and we wanted to monitor their hand washing between patients and for conformance to, kind of hygiene. And the nurses said, we always do it right and we never forget. And no, you're gonna get us fired. So they didn't want to do it. And the doctors wanted to do it because they wanted to help the patients. So we did it with the doctors. And then 5 years, then we had some issues. We took the system out and we went back. And then 5 years later, all the nurses were wearing Apple Watches. And they all said, yeah, let's do this. So, I think the providers will end up doing the same thing, I think, if we do it right and we can show that it's helping them, not making more work for them.
It was a great talk with Jack, and having worked with the neurologist, MD, and hospitals on some smart health, because we also had a smart chair to track the dementia and Alzheimer patients, and actually we have data for more than 280 patients. They're the dementia patients leading to Alzheimer, I don't know. But what challenge that we are facing, I think you covered quite a few things in an integrated, interdisciplinary way. But given all the things that are there, let's say machine learning model, finite state, and all these models that you talked about, control things, and uncertainty handling, noise, and all this, do you think that some kind of new mathematical paradigm will emerge out of this type of, because medical science still has lots of observational things, right? Lots of experiential kind of stuff, not very, I'm just thinking that, do you anticipate some kind of new mathematical and foundational paradigms will come out of it, and that we can handle many of these things in a very systematic way rather than, because you have NLP, all sorts of different things that are there. So that's my curiosity, and we have been actually looking into that. What kind of mathematical invariants can we derive? What kind of foundational things that we can propose that is very unique? Any thoughts on that?
Yeah, that's another really interesting question. And I think in some situations you might be able to do that, and I think in others it may be not amenable to mathematics. Certainly, like if you're talking about image processing and AI, monitoring an X-ray, looking for cancer or something like that, that may be the way that the cancer cells portray themselves can be described mathematically, and you can, kind of be pretty accurate at finding it. Right now, they do a good job simply by data-driven approaches, but if maybe by a more mathematical approach, they can even improve the accuracy. Human behavior and so on, I don't know. I really doubt for at least a long time that there will be any kind of mathematics behind it. At least on the average, there could be, for sure, but I just think it's important to do the personalization too. So, like, why would I care on average people do this when I have cancer? Like on average, I shouldn't have gotten it, but I have it. Like it's that kind of thing. So, it's got a balance between what you can see from populations versus individuals.
Personalization.
Yeah.
And the calibration is very critical over there, right? Like how do you calibrate?
Okay. Yeah.
Thank you.
Hi, thank you for your inspirational talk. The question that I have is, how might, say, a person that has Medicaid or very low resource or access to great medical care access some of, these innovations? And because, certain doctors will work with certain types of patients depending on their insurance. And what about people in rural areas or marginalized communities that they need these things but can't access? Have you thought about how you might be able to do that?
Yeah, that's a very broad question, and I think that the telemedicine stuff we were doing the idea was that to help that where as patients go home to rural areas where there's little access to doctors, that taking a cognitive assistant with them, the smartwatch, which would be given to them by the hospital. It's like a device that goes home. So the cost is, you know, embedded in the treatments and everything, and so they get the smartwatch. Could we get insurance companies to pay for things that would save them money? So we have to convince them that by this technology, people are going to be healthier, or they're going to not need certain things. So you should pay for that technology so that you're going to save money. And if we can convince the insurance company that, then the devices would be available on Medicaid or other areas. And there was one more point I was going to make. Yeah, the other thing is, many people are, you know, still technology afraid, right? So that's why we want to try to make it all voice-based. People can talk, you know, most people. If different issues come up, if a particular patient, you know, lost their ability to speak. But if you don't have to, like the demo I showed, the person on the watch, you know, had to click things, that should all go away. I should just be able to talk and say to my cognitive assistant, you know, I'm not feeling very well today, what should I do? And it talks back. And so they don't have to know technology. They don't have to, you know, install sensors in their house or do anything like that. So I think those kinds of things might mitigate some of the problems you're talking about.
And just as a quick follow-up, even with speech recognition, right, you have different accents and people, different English, right?
Yes,
So.
yes, absolutely. So that's another bullet I should put on there. What works for Chinese doesn't work for English. What works for Southern accents may not work for, but a lot of speech recognition now allows some training, right? So you can train just with a handful of samples, and then it gets incorporated into their particular speech recognition system.
Thank you.
All right.
I think we'll go to the break now.
Okay.
Okay, so I'm going to just cut it off. So if you have a question, you can come up and ask Jack separately, or anyone else who wants to come up. But we do have a break now. I don't know to what time exactly it's in the program, but please go get coffee and break, and then we'll come back for the next session. If you want more questions, but thanks to Jack again. Thank you.